Hey everybody, this is Larry. This is day 16 of the Leetcode December Daily Challenge. Oops, wrong button. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about today's problem, validate binary search tree. So I usually solve these problems live and also do the explanation live. So let me know what you think about this. It's my first impression, so yeah, leave a comment. Okay, so this one is just valid binary search tree. So yeah. So for this one, I think the way that I would solve it, and it's because that I've solved similar problems in the last month or so a lot on both Leetcode and also this other site that I've been using, binarysearch.com. Definitely recommend that. But for these problems, you could do a breadth first search or a depth first search, but the key point is noting the invariant that happens at each stage. And for binary search tree, and some of this is just because binary search tree is something you studied in computer science, so the invariant is a little bit more studied, so you don't have to think about it that much. Which is that I mean, there's these things that are true that they tell you, but another thing that's kind of true that is a superset of this maybe is that yeah, the biggest node on the left side is going to be smaller than the current value. So so if you have an in-order traversal, it's going to be if you have an in-order traversal, it's going to be valid, so that's going to be O(n). But also that, is that good enough? But yeah, but also that I'm just going. I think if I had studied more in computer science, I might have known that whether an in-order traversal is good enough. But I cannot, so, that said, because I cannot prove that, and it may be something, that, especially on a competition, I might have to, do a proof. But without proving it, we just have to find an invariant, which is that the largest element on the left side is going to be smaller than this value, which is smaller than the smallest element on the right side, right? So as long as that invariant is true for every node, then we know we're good. So basically then now we just have to have a function that tell us whether that is good the entire way. So let's start with that. I'm going to do it with in-order traversal, which is a depth first search in my case. Yeah. So given a node, right? So now we want to find three things, I suppose, to make it. I know that we can use a global variable as well, or like a global context variable, but I want to keep things as a recursion type thing so that we can kind of see how that state propagates. And I think it'll be more educational value maybe. But yeah, for this function, what do we want it to do, right? So actually we want it to return three things, as I said. One is valid. And is valid is just whether the invariant holds for this node and or the subnodes. The smallest value of this subtree, and then the third thing is just the largest value of the subtree. And then from these three things, we should be able to tell whether this invariant holds for the entire time. So yeah, so now if node is none, that's our base case. That means that we went to, I don't know, a value that doesn't make sense. So yeah, so invalid is valid. Is it valid? I guess it's valid. So is valid is good, but the smallest value we're just going to we could just use negative infinity, I think, maybe. No, let's just do none. It'll probably be clearer instead of trying to make some sentinel value. But yeah, so then now we have to get out three things, which is left is valid, left smallest, left largest is equal to calling this function on the left, right is valid, right smallest, right largest is equal to DFS node on the right, and then yeah, and so whether this is valid is if it is valid on the left and is valid on the right, and that the current condition holds. So basically, so yeah, so current is valid, node is valid, so is valid is equal to left is valid, oops, yeah, and right is valid, and current is valid, but we haven't solved this part yet. So so yeah, basically what we want is, and we have to do a couple of edge cases just to make sure that, you know, because this could be none. Maybe we can make it so that it's always true, so that this is like always the smallest value or something like that. But let's keep it simple for now, which is that left, let's have a thing called left is smaller, which is equal to left largest is none, or left, or no dot left dot, oops, dot value, oh wait, no, we don't need that, is left largest is less than or equal to, does it have to be unique? I guess it doesn't have to be unique. Well, I guess in this specific example, this has to be less than, so it has to be strictly less than, I suppose. So no dot value, right? And then right is bigger is equal to the right smallest is none, or right smallest is greater than no dot value. So then is valid is just equal to left is smaller and right is bigger, right? So having all of that, then that's all we need, except for now we have to propagate up. So the largest part is a little bit annoying, but yeah, so okay, fine. So smallest is equal to, so now we have to get the smallest number in the left subtree, or the entire subtree, which is always going to be in the left smallest or this value. So it's equal to left smallest. I'm just trying to think about it in a way that it doesn't check for none. I think maybe I could have to use no values, but then I have to explain it. So I think for now this is fine. If it's not none, else smallest is equal to no dot value. We do the same thing to the right side. Oh yeah, now we have to get the biggest number from this subtree. So right biggest or largest. I mix bigger and smaller, larger. So naming things is tough, but yeah. Oops. So then now all we have to do at the end is just return it. So let's return is valid, smallest and largest, right? And then of course we just have to call the function. So yeah, so is valid empty and oops equal, and then now we just have to return is valid. And that's basically all I have. Let's see if it works first. I guess I would have more if I have if it doesn't work. Where's the second case? Okay, there it is. Also I think just some case where all the numbers are the same. Where did that case go? Did I just click on a button or something? Oh, I clicked on, whoops, I probably hit the back button or something. Okay. So, yeah, something like that. Want some code, one node, and I don't know. Okay, so looks good. Hit the submit button. Cool. Yeah, so what is the complexity of this? Well, this is just a depth first search. We look at each, we process each node in constant number of operation. So that's going to be linear time. In terms of space, well, we do use the recursive stack, the core stack. So that's going to be O of H, where H is the height of the tree, which in the worst case is going to be O of N. Yeah, I mean, I think the hardest part about this problem is just figuring out, getting used to this kind of recurrence, and just figuring out the invariant of the problem. The way that I wrote it is a little bit kind of clunky, to be honest, but I just want to go for correctness so that you could kind of see how I would do it. I probably would have done something similar. Maybe if I was going for extra speed, I would have set these to negative infinity and infinity, just so that I don't have to do so many cases. But that's also where if you try to speed, sometimes you make mistakes. But yeah, that's all I have for this problem. Let me know what you think. I think this is a easier problem given the last couple of problems, but still a lot of potential to make mistakes. So anyway, I will see y'all tomorrow and take care. Bye bye.